Scientific notation, significant figures, and rounding. So first we're going to start with some measurement definitions. You should know the difference between precision and accuracy. And because these are not bolded, I'm just going to take a second to bold them. So precision refers to the ability to get the same result every time. In other words, to be able to repeat a result. Accuracy has to do with getting the correct result. So if you look at this bullseye, so let's say everyone wants to get the bullseye, here's the target, and you can see they threw it 3 times and hit over here. So they got the same result every time. So it's precise. But is it accurate? No, because they were aiming for the bullseye, but they got it over here. A practical example of this is if you forget to zero the balance when you're getting a mass of an object. So every time you're going to get the same measurement, but if it wasn't at 0 when you started, it's going to be inaccurate. It's going to be wrong. Here you can see this is precise and accurate. So they got it in the correct spot every time. So it's precise because they got it in the same spot, and it's accurate because it was in the correct spot. This one is imprecise and inaccurate. It's all over the place. So here's an activity that kind of allows you to estimate whether they are precise or accurate. So you can pause the video and try to determine which one each one of these diagrams is. Precise, accurate, both, or neither. So looking at this first one, Archer W, I would say they're pretty precise and they're pretty accurate. So moderately precise and moderately accurate. And why do I say that? Well, they're all kind of in the same spot, so they're getting kind of the same result every time. And it's kind of always in the correct spot. Now we do have some outliers here, but we do have 2, and I would count 3 out of the 4 that are correct. This one over here, they're precise, they're hitting the same spot every time, but they are not accurate. This one over here, they're not precise and they're not accurate. This one has very low accuracy, so one of them was correct, but they are completely imprecise, so they're all over the place. This large graph on the image displays average global temperatures relative to the mean over the past 100 years. So you can see this graph and all the global temperatures rising. The uncertainty is indicated by the last reported digit. For example, when you're measuring global temperatures, the average global temperatures have risen by 0.6 degrees Celsius in the last century. By reporting a temperature of an increase of 0.6 degrees Celsius, the scientists mean 0.6 plus or minus 0.1 degrees Celsius. The temperature rise could be as much as 0.7 or as little as 0.5, but it's not 1 entire degree. The degree of certainty in this particular measurement is critical, influencing political decisions that directly affect people's lives. So we're going to talk a little bit about how to express numbers in scientific notation, taking numbers out of scientific notation and expressing them back in standard notation, and then we'll get into a little bit more of the precision of a measurement. And precision of a measurement has to do with significant figures, or how many decimal places that are reported in an answer. A number written in scientific notation has 2 parts. The decimal part, which is a number that's between 1 and 10. It's less than 10 and greater than 1. And an exponential part, 10 raised to an exponent. The decimal part can only have 1 digit to the left of the decimal. Otherwise, it would not be in scientific notation. So you can't have 12.2 or whatever, because that's not a number between 1 and 10. It has to be greater than 1 and less than 10. And then the exponent times 10 to the whatever the exponent is. A positive exponent means 1 multiplied by 10n times. A negative exponent means 1 divided by 10n times. 10 to the 0 is equal to 1. 10 to the first is equal to 1 times 10, which gives you 10, and so forth. 10 to the negative 1 means 1 divided by 10, and that gives you 0.1. To convert a number to scientific notation, you want to find the decimal point, and then find the exponent. Move the decimal point to obtain a number between 1 and 10, and then multiply that number, or the decimal part, by 10 raised to the power that reflects the movement of the decimal point. So that's written out steps, and a lot of people don't do well with just a series of statements, so I'm going to give you some examples. So if we want to write 5,983 in scientific notation, the first thing is we have to identify where the decimal point is. So in 5983, there is no decimal point. So we're going to put an imaginary decimal point at the end of the number. Then we're going to move it to the left until we get one number to the left of the decimal. So we're going to move it 1, 2, 3 positions. So now we're going to write 5.983, and we're going to times that by 10 to however many positions we moved. So we moved the decimal 3 places, 10 to the third. Here's another example. So now we're moving the decimal to the right. Anytime you move the decimal to the left, you're going to end up with a positive exponent. But if you have to move the decimal to the right, you're going to create a negative exponent. So now we can see a decimal in the number. We're going to move it 1, 2, 3, 4 times. Why didn't we move it 5 times? Well, if we moved it 5 times, we would have 34 instead of 3.4. And we have to get to a number that's between 1 and 10. So we have 3.4 times 10, and then we have the negative 4, because that's the number of positions we had to move it. These 2 points down here are extremely important. So if the decimal is moved to the left, the exponent is positive. If the decimal is moved to the right, the exponent is negative. How to convert to scientific notation. So these are some practice problems. I would like you to pause the video and try to work through these practice problems. In a little bit, when you're done, I'd like you to unpause, and then I'm going to go through these. So hopefully you had an opportunity to figure out all of these problems. So I'm going to talk through the problems here. So here you can see a decimal point, and the decimal point is right here. And we want to get so that the number becomes between 1 and 10. So here's our number, and we want to move the decimal point over 1, 2, 3, 4, 5, 6, 7, 8 positions, so that we have 2.948 times 10, and since we moved it 8 points to the right, we're going to have negative 8. The next one, we don't have a decimal here, so we're going to put an imaginary one at the end, and we're going to move this over 1, 2, 3, 4, 5, 6. Why did we move it 6? Because again, we want a number between 1 and 10. So this becomes 1.29230 times 10. And since we moved it to the left, we're going to give it a positive exponent to the 6. 3,000, we're going to put our imaginary decimal point at the end here. We're going to go 1, 2, 3. So we're moving this 3 positions to the left. 3 times 10 to the third. Here's our decimal. We go 1, 2. So that becomes 1.14 times 10. And because we moved it to the right, -2. Positive exponents talk about really large numbers, while negative exponents talk about really small numbers. So that's another way to remember the left and right rule and whether to write a positive or negative exponent. 1.10 is already in scientific notation. We do not need to add anything to this, it's just 1.10. We can do 1.10 times 10 to the 0. We can just leave it 1.10. So here, going back here, we have our imaginary decimal point at the end, and we're going to move it 1, 2, 3, 4, 5, 6. And because we moved it 6 places to the left, it's 5.345. And you can write the 3 zeros, you can leave them out. Once we get into significant figures, you'll know whether to write them or leave them out later on. So 5.345 times 10 to the 6th. So now we want to convert from standard notation, or convert from scientific notation to standard notation. So I'm going to do the first couple, and then I'm going to ask you guys to pause the video and try the rest of them on your own. So this first one, 1.293 times 10 to the -3rd. So because this is a negative exponent, we want to create a really small number. So we're going to end up moving the decimal point to make this a smaller number. So we go 1, 2, 3. And we're going to put a decimal point here. Now we have to fill in the missing places with zeros. So we're going to put a 0 here and a 0 here, because this took up one of the places when we moved it over. So the number becomes 0.001293. So with this next one, we're going to write out the number 5.3982. And now we're going to move our decimal. We're going to move it 4 times, and we want to make the number bigger because it's a positive exponent. So we're going to move the decimal 1, 2, 3, 4, because we want to make the number bigger. And this becomes 53,982. I'm going to ask you now to pause the video and work on these last 4 problems here. When you're done, in a little while, you can unpause and I will go through the answers. Okay, so hopefully you had a chance to work on that. So we have 8.70000 times 10 to the -5. Negative means we want to make this number smaller. So 1, 2, 3, 4, 5. We're going to have to fill in 4 zeros. And we go 0.12348700000. So that is the number written in standard notation. So here's another one. We have 3.0900, and we're moving that decimal 3 places to make the number bigger. 1, 2, 3. So that becomes 3,090 0.0. Here we have this number, and we're going to move it 2 places to make the number smaller. 1, 2. So it's going to be 0.022901800. And here we have the number, the decimal, and we're going to move it 6 places to make the number bigger. 1, 2, 3, 4, 5, 6. So we actually have to add 2 zeros at the end. So that becomes 4, 0, 0, 9, 0, 0, 0. And that's our number in standard notation. There will be some additional practice problems on your homework assignment, and then if you have any additional questions, please bring these up in class. So pennies come in whole numbers, and a count of 7 pennies means 7 whole pennies. Our knowledge of the amount of gold in a 10-gram gold bar depends on how precisely it was measured. So when we report scientific numbers, we have a certain part that's certain, so we know for sure it's that at least, and then the last digit is typically estimated. It's not always going to be the first 4 digits are certain while the last is estimated. Every number is going to have a different number of certainty versus estimated numbers. The greater the precision of the measurement, the greater the number of significant figures. So the more decimal places that we can give in a measurement, the more precise that measurement. This balance has markings every 1 gram. We estimate to the 10th place. So to estimate between the markings, mentally divide the space into 10 equal spaces and estimate the last digit. The reading is 1.2 grams. So we don't know for sure that this is 0.2 grams. We know that the first line is 1 gram, and we know that it's a little bit beyond that first gram. So we're estimating it looks like it's about 0.2 grams. So that's what we write down. But the 0.2 is an estimation. The 1 is for sure. This scale has markings every 0.1 gram. We estimate to the hundredths place. The correct reading is 1.26. Significant figures include both the certain part of the measurement as well as the estimate. And there's some rules for counting significant figures. The first rule is all non-zero digits are significant. So any whole number is significant. 21.2 has 3 significant figures. An exact number has an infinite number of significant figures. So if there's 35 pennies, there's 35 is significant. If we say 350 pennies, 350 are significant. Defined numbers are also significant. There's 12 inches in 1 foot. Zeros are typically not always going to be significant, but a zero can be significant when it is between non-zero digits. So 403 has 3 significant figures because that 0 is sandwiched between non-zero digits. At the end of the number, that includes a decimal point. 0.050 has 2 significant figures. The significant figures are not the first 2 leading zeros. The 5 and the 0 are the significant ones. Two 2.0 has 3 significant figures because it's at the end of the number that includes a decimal point. 20 point has 2 significant figures because, again, it's at the end of a number that includes a decimal point. How many significant figures are found in 3.040 times 10 to the 6th? So using our rules, this and this are automatically significant because they're non-zero digits. This is a zero sandwich, so it's significant. And this is at the end of a number that contains a decimal point, so that one's also significant. So there are 4 significant figures. A 0 is not significant when it is before the first non-zero digit. So here, 0.0043 only has 2 significant figures. So this one and this one are significant. A trailing 0 in a number without a decimal point. So 2400 has 2 significant figures. If I would like to make those zeros significant, I'd have to add a decimal point. But as written, the 2 and the 4 are only significant. 9010 has 3 significant figures. The 9 and the 1 are non-zero digits, and that makes them significant. This makes a zero sandwich, and this is a trailing 0, which does not count. How many significant figures are found in this number? Well, we have the 5 and the 6, and then anything before the whole numbers is not significant. So this one only has 2. Why does it only have 2? The leading zeros are not significant. Let's say we measure the width of a sheet of paper, 5.6 centimeters. The 5 was certain and the 6 was estimated. The length in meters is 0.056 meters. We use significant figures rules to be sure that the answer is as precise as the original measurement. So I'd like you guys to pause the video and go through and try to answer how many significant figures are in each number. In a little bit, you can unpause and I will go through the answers with you. Okay, so if we go through the answers together, leading zeros are not significant, so these 2 whole numbers are significant. This one has 2 significant figures. Here we have 2 non-zero digits, we have a zero sandwich, and then we have a 0 at the end of a number that contains a decimal. This has 4 significant figures. These are all non-zero, so this is going to be 4 as well. 2.9, this is going to be 2. 1 dozen equals 12. This has, the number 12 has 2 significant figures because it is of a known quantity. 100.00. So because these are trailing zeros in a number that contains a decimal point, we have 5 significant figures here. And because these are trailing zeros in a number that does not contain a decimal point, we just have 1 significant figure. Rules for rounding. So when numbers are used in calculation, the result is rounded to reflect the significant figures of the data. For calculations involving multiple steps, round only the final answer. Do not round off between steps. This is extremely important. Sometimes, later on in the semester, we're going to end up with 4, 5, 6 step math problems, which don't freak out right now. I promise I'll make them really practical and easy to follow. But if you round in between each one of those steps, you can see how those rounding errors are going to really add up to something significant. So we never want to round until the very final answer. Use only the last or leftmost digit being dropped to decide in which direction to round. Ignore all other digits to the right of it. Round down if the last digit dropped is 4 or less, and round up if the last digit dropped is 5 or more. So it wants you to round 240391 to 4 significant figures. So we go 2, 4, 0, 3, 9, 1. So we want it to have only 4 significant figures. So we're going to count 1, 2, 3, 4. And we're going to look to the right here. We know that we don't want any numbers to go beyond that point. So is 9 5 or above or 4 or below? Well, obviously 9 is 5 or above. So we're going to take this 3 and round it up to a 4. So our final answer will be 2404. And then we have to add 2 zeros as placeholders because we can't all of a sudden round and then drop down to like a number that's in the thousands. This is one of the biggest mistakes that I see on exams, assignments, quizzes, all that type of stuff, is that students will round a number and just delete the last digits like they never existed. The number as written now has 4 significant figures. It has the 2, 4, 0, 4, which are significant. And these last 2 zeros are trailing zeros in a number that does not have a decimal, so those are not significant. We now have 4 significant figures, and the value is maintained. So we have 240,000 something, and we still have 240,000 something. That's something that you always need to check when you're done rounding. Does the value of my number still make sense? And if it doesn't, you want to make sure you add the zeros so that it does make sense. So now it's telling you to round each of the following to 3 sig figs. I'm going to give you a chance to work through these. When you're done working through them, I'd like you to unpause the video and then we will go through them together. Okay, so let's look at this first one. We want each one of these to have 3 significant figures. So these leading zeros are not significant, so we have 1, 2, 3, and then we have to look to the right. We know that we are going to not have any number here because if we did add a 0 or anything else, that would change how many significant figures that we have. So 9 is 5 or above, so we're going to round that 2 up to a 3. This becomes 0.00393. We are not going to add another 0. Adding a 0 means that we would have 4 significant figures. We're not going to do that. We only want 3, and this is what we're going to go with. So here's a number 2999. We want 3 significant figures, so 1, 2, 3. We're going to look to the right, and we know that we have to round this up. So this becomes 3,000. 3,000 as a number has 1 significant figure. If you know from the rules, these zeros are not significant because they're trailing zeros on a number that does not contain a decimal point. So we have to make sure that we have 3 sig figs. So even though the number 3,000 is correct, 3,000 as a number does not have 3 sig figs. Also, we can't just add a decimal at the end or in the middle, because doing that, adding a decimal changes the value of the number. And then adding a decimal at the end would change it to 4 significant figures. So how do we figure this one out? The only option is to convert it to scientific notation. So we put our imaginary decimal there, 1, 2, 3. 3.00 times 10 to the third now has 3 significant figures because these are trailing zeros in a number that has a decimal point, and that's 3 sig figs. Now we want to make the number 100 have 3 sig figs. Well, if we add a decimal at the end, now these zeros became significant. If we want to round 1,000 to 3 sig figs, we go 1, 2, 3. We look to the right, and it's a 0. But we can't just drop that 0. We can't round 1,000 down to 100. That doesn't make sense value-wise. So same thing to up here. We need to actually convert this number into scientific notation in order for it to be 3 sig figs. So we put our imaginary decimal at the end. 1, 2, 3. That becomes 1.00 times 10 to the third. Here's another example. 1, 2, 3. We look to the right, and it's 0.9, and it's 9. So 9 is 5 or above. We're going to round this to 0.731. We don't have to add anything else because we'll just drop that. Since it's at the end of a decimal, it would make those significant. So we're going to leave it how it is. 54.50. We want to make this 3 sig figs. We're going to keep 1, 2, 3. We're going to drop the 0. 54.5. We started with a number that's 54, and we're ending with a number that's 54 point something. So the value of the number did not change by dropping that 0. Here we go. We want to round this to 3 sig figs. Nothing significant until we get the first non-zero. So we got 1, 2, and these are significant because they're at the end of the number that contains a decimal. So this to 3 sig figs is 0.00099, and then we will drop the last 0. Dropping the last 0 in a number that has a decimal does not change the value of the decimal. The multiplication and division rule. So the result of multiplication or division carries the same numbers of significant figures as the factor with the fewest significant figures. So if we want to multiply 5.02 times 89.665 times 0.10, we actually get this as a number. But this number has the fewest number of significant figures, so our answer has to be expressed into significant figures. Here's another example. We have 4 significant figures divided by a number with 3 significant figures. It gives us this as an answer. But because this number had the least number of significant figures and it's a multiplication or division problem, our answer has to have 3 significant figures. So our answer is going to be 0.966. So we rounded this one to 3 sig figs. The addition and subtraction rule says that in addition or subtraction calculations, the result carries the same number of decimal places as the quantity carrying the fewest number of decimal places. So in adding and subtracting, we just count the number of decimal places, not the number of significant figures. So if this number has 2 decimal places, this number has 3 decimal places, this number has 3 decimal places, we want to make sure that our answer only has 2 decimal places. And we're going to round it so that it has 2 decimal places. So here's an example. 4.8 minus 3.965 gives us 0.835. We're going to round it to the number of decimal places of the least number of decimal places in out of 4.8 and 3.965. In calculations involving both multiplication and division and addition and subtraction, do the steps in parentheses first, determine the correct number of significant figures in the intermediate answer without rounding, then do the remaining steps. So in this calculation, you're going to do the step in parentheses first, use the subtraction rule to determine that the intermediate answer only has 1 significant decimal place. Then you're going to multiply, and then you can figure out the number of significant figures from there. So to review multiplication division problems, figure out which measurement in the problem has the lowest number of sig figs and round your answer to this number of sig figs. In addition and subtraction problems, figure out which number has the lowest number of decimal places and then round your answers so that it has that number of decimal places. In this class, I would like you to round all of your answers to 3 sig figs unless you're told otherwise. So there will be some challenge problems on the upcoming test that tell you to round to a specific number of sig figs, but instead of remembering all these rules and trying to keep track of this as the semester progresses, I would like you to just round everything to 3 sig figs unless it specifically tells you to not do that. You do need to know the multiplication and division rule, you need to know the addition and subtraction rule, but for the purposes of this class, all your lab answers, all your test answers, everything that you produce for me in this class, we'll just keep it simple and it should have 3 sig figs in the answer.